Hello, everyone, and welcome to this episode. Today, we are talking about factors that affect solubility, specifically three of them. Lately, we've been learning about chemical equilibrium and how some things are very soluble and some things are not very soluble. But even though those things that are technically not soluble or insoluble actually do dissolve to a certain extent in water, and we have equilibrium constants for those. We call them solubility product constants. And today, we're looking at those solubility product constants and also for ways to either help the thing dissolve a little bit better than it could on its own or dissolve less than it could on its own. And so there are three factors. We're going to get to those. We'll start with this. I'd like to show you some data to kind of get you thinking about this. This is the solubility of calcium fluoride in different sodium fluoride solutions. In a previous video, we did a couple of these calculations, and I have a couple samples here that I've already worked out for the sake of time. But if the sodium fluoride concentration is zero, like if it's just pure water, the calcium fluoride will dissolve to a certain extent. But as you add sodium fluoride to that water, to that solution, the calcium fluoride dissolves less and less and less. And that is due to the presence of the fluoride ion that is in there already, and it's trying to dissolve even more into it. I have the calculations worked out. Let's check them out real quick. If you need to pause the video, you totally can. And here's our dissolving dissociation equation. And we're going to do pure water first. I rewrote the equation, our ice table, x and 2x. Here's our KSP expression. And the KSP value for calcium fluoride is around 4.0 times 10 to the minus 11. I plugged in x and 2x and squared it. That simplifies to 4x cubed, and I got an x value, or a molar solubility, of 2.15 times 10 to the minus fourth moles per liter. So not a lot dissolves, but it's immeasurable, and we can account for that. Now let's see what happens if we choose the 0.1 molar sodium fluoride solution and repeat the same calculation. The only difference here is that the initial value for the fluorine is now 0.1 and not 0. And so we actually have something in there that it's trying to dissolve into. And we get an x, and then, 2x, 2x, and a 2x. Sorry about that. Don't do what I did. And but this 0.1 value is actually very, very large compared to what x is going to be. So I'm actually going to drop the 2x's anyway. And I do the math, and I get a molar solubility of 4.0 times 10 to the minus 9th, which is a lot smaller than the 10 to the minus 4th that's there. And you can see by the graph that if we go over to 0.1 moles per liter and down, we're way down here at the bottom as opposed to several factors of 10 higher at the beginning. So this is all evidence of the first factor that affects solubility, and that is the common ion effect. This is a repeat slide from a previous video. If you want to check out the common ion effect video, feel free to go there and then come back if you want. The common ion is an effect that suppresses the ionization of an electrolyte when another electrolyte, which first contains an ion also present in the first electrolyte, is, i.e. a common ion, is already present in the solution. That dissolving of the new thing is hindered and reduced. And we saw that by the calculation and the graph. So that's the first one. Now, to give you an idea where we're headed, there's three factors. We just kind of talked about the first one, the common ion effect. We're going to now talk about the effect of pH on solubility and also the formation of complex ions, which you're likely to see if you hang around the chem lab long enough. So let's look at another graph. I'm keeping calcium fluoride as somewhat of a theme here today. And it's a similar shape graph, but it's a different graph, different data. And we're starting here. And if you imagine a pH of 7, the pH value is going from 0 to 7. At 7, pure water, we're not getting much dissolved. And then as we go to 6 and a 5 and a 4 and a 3, we're getting a little bit more dissolved. And then finally, when it's very acidic solution, we get a ton of dissolving. And it's amazing. And this is actually times 10 to the third moles per liter. So we're talking a huge number of moles will dissolve at a low pH. And so the question becomes, why? Why did calcium fluoride dissolve more at the low pH? There are some salts that will be affected by the pH and higher or lower. One is it's all about the anions. One is if the anion is OH, hydroxide, which is a major player in aqueous solutions, acid-base solutions. If the compound has hydroxide in it, it will be affected by pH. And if the anion is the conjugate base of a weak acid, salts with anions of strong acids, chlorine, bromine, and nitrate, for example, are unaffected by pH changes. But if the salt has an anion that is the conjugate base of a weak acid, then it's likely going to be affected by pH. We may need to do a quick review of strong and weak acids. Here we go. Strong acids are those that are 100% dissociated. The anions will not reaccept the protons. And so hydrochloric acid just breaks apart 100% of the time, and those are just going to be floating around in solution. And that chloride ion has no desire to get back together with the hydrogen. It's a very weak chemical bond. Water just broke it up, and they're not going to reform. Hydrofluoric acid, on the other hand, is only partially dissociated. That fluoride ion actually would prefer to be back with the hydrogen. It'll dissociate some and set up a little equilibrium, but for the most part, most of the HFs are still HFs. They're not dissociated. And that has a fairly low Ka value. Okay, so let's start with an example of a hydroxide compound. So a hydroxide compound like magnesium hydroxide, for example. All right, and here we are going to dissolve some magnesium nitrate in distilled water. Getting some white precipitate here with the magnesium hydroxide undissolving. A little hydrochloric acid goes in. And cleans that baby right up. And magnesium hydroxide is fairly insoluble in water. It'll dissociate into some magnesium and 2 hydroxide ions, and they'll set up a little equilibrium and hang out for a little while. If, however, I change the pH, let's say by adding some hydrogen ions to it, adding some acid, getting some protons floating in there, and lowering the pH. When that happens, you introduce the hydrogen ions, protons. They're going to gobble up some of those hydroxides and make waters because that's what they like to do. These two put in the same room will most likely make one of those. And by making a water, we essentially drop out some of the product, the hydroxide. And then this new equilibrium system says, hey, wait, we don't have enough hydroxides. Let's dissociate a little bit more and make some more hydroxide that I just lost. And that means more of this is going to dissolve. The overall reaction here is the MgOH2, if we add up these two equations, plus the two OH pluses, will make magnesium, and the two waters, the two OHs will cancel on both sides of this. And that's our net overall equation. Okay, so adding acid to a hydroxide increases its solubility, and including a lot of hydroxides, like nickel hydroxide, would make a precipitate because it's not very soluble. But once we add some hydrochloric acid to it, it will redissolve and go back to being nickel ions in solution. And let's look at the conjugate, or the anion that's the conjugate of a weak acid, the fluoride ion. Here's our graph. I made it a little smaller. And it says here, if the anion is the conjugate base of a weak acid, added hydrogen reacts with it and removes it from the equilibrium, causing more salt to dissolve. And so I put the reactions over here. So calcium fluoride making calcium and fluorine. If I add protons, lowering the pH, adding some acid, those hydrogens and those fluorines will get together because they will form a weak acid then, making that, which is not part of my original equilibrium, but it does drop this out of the equilibrium. And the overall reaction now is calcium fluoride reacting with the acid to make more aqueous calcium ions and a couple of HFs out the other side. So adding an acid to an anion that's the conjugate of a weak acid will cause more dissolving to occur. That's a lot. So if you want to take a moment and process that, that's fine. I did summarize it on the next slide here. So salts containing the anions found in strong acids like chloride, bromide, iodide, nitrate, sulfate, and perchlorate, those are not really going to be affected by pH at all because these ions don't want to grab those hydrogens and do anything with them. So keep a note of those. Those are the conjugates of the strong acids. But salts containing the other anions, fluoride, carbonate, etc., and that are conjugates of weak acids, will be affected by pH, and for the same reason. Okay. And let's look at the last one here, the last factor. and which you may or may not have seen before, but we're going to be talking about a little bit about complex ions. Okay, and complex ion formation. So what happens here is that metal cations get into the party here a little bit too if they come in contact with a Lewis base. Now you might be wondering, what the heck is a Lewis base? I know what a Bronsted base is. That's a proton acceptor, and a Bronsted acid is a proton donor. But Gilbert Lewis came up with the definition that an acid is more of an electron acceptor in some cases, as opposed to a proton donor. In either case, they're getting more negative, but you can actually accept electrons and give electrons, and that's acid-base properties. And Lewis bases are electron pair donors, so they're molecules or ions that actually have lone pairs they can donate fully to make a chemical bond of some kind. These are called ligands, and they help form complex ions. When a metal ion forms a complex, it leaves the equilibrium system, and the salt dissolves more to replace it. All right, so let's see how this works. If I were to take some copper ions in solution, you have copper 2 plus, they're positively charged, they're floating around, they're probably hanging out with the negative ends of some water molecules and so on. And if I add some ammonia to it and put those ammonia molecules in it, what we end up getting is a complex ion where the ammonium or ammonia does this 4 times with its trigonal pyramidal structure and a lone pair sticking out on the outside. They will form little attachments to that copper ion. And if 4 of them do this, you will get a complex out of it. And we'll put the nitrogen there. And this whole thing becomes a big coordinated system all together. It will still have a +2 charge because the copper hasn't lost its charge and these are all neutral. But now they're going around as a unit, and they're not just single copper ions anymore. And so now the copper ion actually, which might be insoluble in some cases, can actually be soluble and move into the solution. Let's look at an example. Some silver chloride. And silver chloride is insoluble for the most part, although a tiny amount of it does dissolve. But if I have the silver chloride and I want to get it to dissolve, one of the things I can do is add the ammonia to it in the same way as I might add it to the copper. And what the silver ion does is it forms 2 attractions to 2 ammonia molecules. All right, and this becomes a complex ion with a +1 charge. And this is the diamine silver 1 ion. And because that's not part of the original equilibrium system, more silver chloride will dissolve in order to take its place. And that way we can help the silver get dissolved again. So the formation of a complex ion with a metal cation, changing the pH so that the anion has a chance to get into the game, and the common ion effect are all 3 different ways that the solubility of a salt could be affected, either positively or negatively, depending on what your goal is.